Scott doesn't need that much of an introduction. We're a very well-known figure in computational complexity broadly and the world expert in quantum computing. And he has a very popular blog. Done wonderful research, and we'll talk about some of the recent work he's been doing. So thank you so much for coming, Scott, and giving it up.
All right. Well, thank you a lot. I mean, Princeton is in a really special place to me. It is wonderful to be back here. I actually did not know until this morning that the Princeton CS Theory had relocated to this, these cool digs in this realty building. Okay, but I really like it. It has a startup feel to it. Okay. All right. Don't get attached to it. All right. Yeah. So I've been actually, traveling for several weeks, giving talks about quantum supremacy. Someone the other day called it my Gil Kalai was wrong 2020 World Speaking Tour. Okay, this is just by way of saying that the slides that I have are sort of a little bit more for like a general audience rather than a TCS audience. So what that means is just that I'm going to go quickly through stuff that probably a lot of you already know, and if there are more technical questions, then we'll just go to the whiteboard. All right. So sound good? So yeah, when you do a Google image search for quantum computer, this is what comes up. Obviously I am very far on the theory side. I was, not part of the amazing team of 75 people at Google that did this quantum supremacy experiment that you probably heard about a few months ago. But I have toured their lab. I've toured enough of their labs to tell you that's not exactly what they look like. All right, so here's my one-slide summary of what quantum computing is. Excuse me, I'm also recovering from a cold, so forgive me. But if you've got a classical probabilistic algorithm, let's say a BPP algorithm, right? It has a state. Let's say it's a collection of n bits. I can do logic gates on the bits, and I can also do probabilistic operations, like set the first bit to be 0 or 1 with equal probabilities. Okay, and if I do that, then I will get, you could say, a general state that I could describe by a vector of 2 to the n probabilities, one for every possible string. Okay, and then at the end I look at the computer to see an output, and the probability that I see a given output string, say x, is just a sum over the probability of every possible path that could have led to that output string, right? And in turn, the probability of each path can be computed as the product of the probabilities of all the choices that were taken along that path, right? And that is all kind of pedantic, but it's I said it because if you understand it, then quantum mechanics is just that, but we replace the probabilities by complex numbers. Okay, so the central thing quantum mechanics says about the world is that if we've got any kind of physical system, we could see it in different states when we look at it. Then it can also be in a complex linear combination of those states that we call a superposition. Okay, so we assign a complex number now, which we call an amplitude, to each possible state. So we could have a superposition where there's 1 over square root of 2, let's say 0, 0, I over square root of 2, 1, 0. Okay, so we have, in general, a quantum computer would be a device that would be made out of n basic building blocks that we call quantum bits or qubits, which are just bits that can be in a superposition of the 0 state and the 1 state. Okay, but the key point is that if you've got n qubits, and if they can interact with each other, they can form an entangled state, meaning that we need not just amplitudes for each qubit separately, but we need a vector of 2 to the n amplitudes. Okay, 1 for each string. This will be a unit vector. Okay, and then the rule is at the end, when we measure, the probability that we see a given string will be the squared absolute value of its amplitude. Okay, and the amplitudes are, once again calculated by summing over a contribution from every possible path through the, non-deterministic computation that could possibly have led to that output. Okay, but now this brings us to sort of the key point of quantum mechanics, which is that, before we measure, the amplitudes obey different rules than classical probabilities do. Okay, and in particular, being complex numbers, they can cancel each other out. They can interfere with each other. Okay, if an event could happen in one way with a positive amplitude and another way with a negative amplitude, the two contributions can cancel. The event has probability 0. If I blocked one of those paths, then the amplitude would become positive or negative, and so then the event could happen. So to summarize, by decreasing the number of ways for a thing to happen, I can increase the chance that it happens. That's interference, right? And basically anything you will ever read about the weirdness of the quantum world, if it's not lying to you, then it is just yet another implication of this change to the basic rules of probability. Okay, replacement of probabilities by amplitudes. And in particular, and the real change is that we use these cats around the, to remind ourselves that we're talking about quantum states. Just a notation for vectors, okay? And now the key point with every quantum algorithm is that we are trying to choreograph a pattern of interference that concentrates a large amplitude onto the answers that we want. Okay, so what pretty much every popular account of quantum computing will say is that it's just a way to try every possible answer in parallel. The trouble with that story is that, well, while it's easy to create an equal superposition over all the possible answers, even say to an NP-complete problem, if you just did that, not having done anything else, then when you look at the computer, this rule tells you that what you'll see will just be a uniformly random answer. And if you just wanted a uniform random answer, well, you could have picked one yourself with a lot less trouble. Okay, so the entire point is to choreograph things so that for each wrong answer, the paths leading to that answer have interfere with each other, point in different directions, mostly cancel, and for the right answer, you get constructive interference. The paths leading to that all have amplitudes that are pointing in the same way. Okay, if you can do that, then you measure the right answer is observed with high probability. Okay, that is what Shor figured out how to do for factoring. It was not trivial. That's why why it took Peter Shor to do it. Okay, and what Grover did for searching a list of size n and square root of n time. That will also be behind the quantum supremacy experiments that I will talk about today. Okay, so so how do we actually build a quantum computer? Well, sort of the abstract logic of qubits that I summarized in the previous slide could be physically instantiated in many, many different ways, all of which are right now being explored in parallel by a bunch of startup companies, Google, Microsoft, IBM, and academic labs, other players. And so one approach is to use, excuse me, is to use atomic nuclei, use their spin states as their qubits. So spinning clockwise would be a 0, spinning counterclockwise would be a 1. You can have superpositions of the two. These are individual ions that are actually individual nuclei that are being imaged. You can trap them in a magnetic field. You can move them around with lasers to make them interact with each other, produce entangled states. This startup IonQ in Maryland is pursuing this. Now Honeywell also. You can also use neutral atoms, as in the group of Misha Lukin at Harvard. You can use photons, like polarization states or other states of photons to represent qubits. Psi Quantum, a startup in Palo Alto, is now aggressively pursuing that. Microsoft is taking an approach that you could say is a big big gamble even by the standards of quantum computing, okay, which is called topological qubits. Okay, if this works, it could have, enormously better scaling properties, which is why everyone is so excited about it. So far, people have succeeded in creating exactly 0 topological qubits. But, we hope that eventually Microsoft or someone else will succeed. All it requires is creating a new state of matter that has never been seen before. Okay. Now, the approach that has been most in the news lately, and the one that I will focus on mostly today, is superconducting qubits. This is what is being pursued by Google, also by IBM, also by various startups. Okay, and this is where we create a chip, which is just the size of an ordinary microchip. On the chip are a bunch of superconducting coils of wire. Okay, and current can flow through these wires in 2 different states, which representing a 0 or a 1, and Now what we do is we put that chip into a dilution refrigerator that cools it to about 10 millikelvin, okay, about 1/100th of a degree above absolute 0. That's this upside down wedding cake here. That's the dilution fridge, okay, and that causes the bits, the currents to actually superconduct and behave as qubits, so they can be in superpositions of the 2 different current states. They're arranged roughly in a 2D square grid. Each qubit can interact with its neighbors, with its nearest neighbors. Okay, and better yet, you can send control signals from a classical computer that is outside the dilution fridge that tells each qubit exactly what you want it to do when. Okay, so it's a fully programmable device. In principle, if the qubits lasted long enough, it could do a universal quantum computation. Doing each operation on 1 or 2 qubits takes only about 40 microseconds, so it's pretty fast. Doing a bunch of layers takes 40 microseconds. To do an individual operation takes some nanoseconds. Okay, so you have fast operations. You can measure the states of the qubits in the 0-1 basis. I should mention that these are enormous by the standards of qubits. By enormous, I mean that you could see them with a magnifying glass. Okay, so these are actually collective states of many billions of electrons flowing around these little coils. And the reason why something that large can behave quantum mechanically at all is, first of all, this ultra low temperatures, and secondly, the superconductivity. Okay.
So how long
yeah.
would they last?
So how long they last right now is about 40 microseconds. Okay, so that is not a long time. It doesn't sound like a long time, but again, compared to the gate times, it's not that bad, right? We can get in, a good number of layers of operations before we lose the quantum coherence. Okay, and so that's not nearly as many as are wanted, enough to just this summer get to quantum supremacy. Okay, so I will tell you all about that.
What's the connectivity?
Good. Yeah. So it's more or less just like a square grid. It's more or less a square grid. It's not. I think it's not exactly that, but it's.
So you got
yeah.
constraints because of that fact.
Absolutely.
Arbitrarily interaction.
Well, yeah. So we could say, in principle, if there was no limit on circuit depth, then then nearest neighbor connectivity is fine, right? We can simulate an interaction between any 2 qubits by simply doing a sequence of swaps, right, to bring the one to the other and back, right? But yeah, of course, we're then paying a large overhead. So yeah, so it is an issue. You could say, ultimately the issue arises from the 3-dimensionality of the space that we live in, right? And but just like with classical computing, a lot of the time is ultimately going to be spent just bussing data around, right? That is in some sense unavoidable. Yeah.
Account in terms of the theory of what you can do with a quantum computer.
Absolutely, yes. So you could say it has no effect on what is computable in polynomial time. Has no effect on like the complexity class BQP. But if you want to know what you can do in linear time, right, or what you can do super efficiently or within a given depth, then certainly it does affect that, and that is relevant for a lot of things that people want to do in the near term, and it will be relevant for the quantum supremacy experiments that I'll talk about. Okay. Yeah, so why is building a scalable quantum computer, so damned hard? Well, the central reason, which was understood from early on, is decoherence, which basically means just unwanted interaction between the quantum computer and its external environment. I said before, when you look at a quantum computer, you sort of collapse its state. You get a single probabilistic outcome, each one with the probability equal to the squared absolute value of its amplitude. So if I measure a qubit, to ask if it's 0 or 1, I force it to decide one or the other, and then this, superposition is then gone. But crucially, it does not have to be me or any conscious entity that is measuring it. If the information about whether that qubit was a 0 or a 1 were to leak out into the external environment in any way, into the radiation or the air molecules in the room or anything, then it is as if that qubit has been measured. Okay, and so what that means is that if I want my qubits to continue to behave as qubits, I have to keep them incredibly well isolated from the whole rest of the world, but they can't be perfectly isolated or they just sit there doing nothing. So I have to actually get them to interact with each other. Not only that, but in a very precise way. And these requirements are so daunting that there were distinguished physicists and computer scientists in the 90s who said this can never be done. There must be some law of physics that will just prevent this. Now, the big discovery that convinced most of us that it is ultimately only a matter of decades of engineering or whatever was the discovery of quantum error correction and quantum fault tolerance in the mid to late 90s. And basically what this said is that you don't have to perfectly isolate the qubits. You only have to very, very, very well isolate them. Okay, and as long as the rate of interaction between each qubit and the environment is sufficiently small, then you can encode the information you care about by clever quantum error correcting codes across the collective states of many qubits. So in such a way that even if a small fraction of the qubits leak out their states, we can detect that and we can recover what we need from the remaining qubits. Okay, and keep continually doing that. And basically what happens is that if the physical error rate is high enough, then doing all of this is only going to make things worse, right? Because the error correction circuitry will itself have error and so on. But when the physical error rate gets below some threshold, then it becomes a net win. It starts making things better, and then it's it's kind of like the AI singularity, right? It's like once it's it's better, then your better qubits can in turn simulate qubits that are better still, and so forth, until in principle you could maintain the qubits for an arbitrarily long time and do an arbitrary computation on them. So we are still pretty far from achieving that threshold for fault tolerance. On the other hand, the experimentalists are orders of magnitude closer to it than they were when they started doing this stuff 25 years ago. Okay, so it is it is now looking a couple more orders of magnitude and you're there, right? So now, but to be clear, the achievement of quantum supremacy that you've read about was not the achievement of error correction or fault tolerance. In fact, everything that has been done so far in quantum supremacy has been with totally non-error corrected, bare physical qubits. Okay, the way I like to describe it is that we are still waiting for the quantum computing analog of the transistor. Okay, maybe that will be topological qubits. Maybe someone will just power through and do these massive amounts of error correction that could also get us there. Okay, but in the meantime, I would say that with quantum supremacy, we have finally entered the very, very early vacuum tube era of quantum computation. Okay, so yeah.
Do we know what's measuring the quantum bits? I'm assuming for each technology there are...
Exactly. For each one, there are different ways of measuring it. But I mean, at a high level, measuring involves taking a qubit and coupling it to some macroscopic, recording system. Like, for example, for a photon, it could be like a photomultiplier, right? Something that just, causes one photon to start like a cascade, right, of an exponential sort of reaction that will just sort of record the state of that photon, ultimately in the memory of a classical computer, right?
Well, what nature measures?
So what? I mean, every at a high level, measurement, you could say means an interaction that sort of takes the quantum system that you're trying to measure and that entangles it with a measuring apparatus.
I'm trying
So
to place a quantum computer over photons. What's
Yes.
the problem? What's going to measure my photon?
What's going to measure your photon is going to be what we call a photodetector, right? Which is a piece of physical apparatus that is sensitive to an incoming photon, and
Would I have it in my lab?
well, if you were a quantum optics person, then you would. Yeah.
We're worried that it gets measured all the time.
Oh yeah, right. So I mean, of course, you want to measure your qubits once the computation is done.
Yeah.
What you don't want is for let's say for example, with Google's device, you are sending these control signals from your classical computer, right? By the way, those control signals themselves need to be cooled down, right? They are sort of hot, right? If they are too hot, they cause decoherence, right? Basically, everything you are doing to control your system is at the same time creating a potential for decoherence, okay? Because it is coupling your qubits to some large, external device, and is creating potential for the qubit state to leak into that external stuff. So that's the high level picture. If you want a more physics and engineering answer, well, you should bring John Martinez or bring people from the Google team to give a talk. Okay. Yeah. So okay. So fault tolerance will require very precise control over the qubits, of a sort that that does not look likely in the near future. Okay, but what can be done in the near future or today? Well, this brings us to this milestone called quantum supremacy, quantum computational supremacy. This term, this is a picture of my friend, physicist John Preskill, who coined this term in 2012, and I'm showing him because if anyone finds the term quantum supremacy to be offensive, then do not blame me, blame him. Okay, he's the one who coined it. Some people have advocated recently changing this term, but the alternatives that have been proposed have been things like quantum inimitability, inability to imitate. I think too many. Not enough people will be able to pronounce that, or also quantum ascendancy. But that to me that just sounds like we're like a UFO cult. We're like ascending to a quantum computer in the sky. So all right.
To use a term that is offensive. I mean,
what?
If you use it, you should stand behind it.
All right, fine. I'll stand behind it. I'm going to use this. I'm going to use Preskill's term. Okay. So in this talk. So, all right. So what Preskill meant by it, and what I also will mean by it in this talk, is the use of a quantum computer to solve some well-defined computational problem faster than any available classical computer running any currently known type of algorithm, let's say, right? And of course, I have to include this caveat about any currently known algorithm, because otherwise this would all have to wait for someone to prove at the very least p is not equal to p space, okay? We can only, if we want statements about exponential speedups of quantum over classical, right? They will all be dependent on some sort of beliefs about complexity theory, about what is intractable for classical computers, and the goal will just be to base things on beliefs of that kind that are as reasonable as we can make it. Okay, so. Notice that I did not say anything about usefulness, okay? So the problem does not need to be useful, okay? Think of the Wright brothers airplane, think of, Enrico Fermi's nuclear chain reaction, right? They were not useful in themselves, they were built to prove a point, okay? But on the other hand, the problem does need to be well defined, right? I mean, the way I like to put it is, suppose someone came along and said, well, I just have this complicated molecule that I'm dealing with in my chemistry lab, and no one can simulate it, even using supercomputers just because of the size of the wave function. So I'm going to define my molecule to be a quantum computer that achieves quantum supremacy for the problem of simulating itself. Okay, I'm going to say no, that doesn't count. Okay, first of all, because your device is not programmable. Okay, so it just does the one thing it does. I can't program it to solve an arbitrary instance of a general problem in the sense of theoretical computer science. Okay, but secondly, I need an external standard of what the thing is supposed to be doing, such that I could in principle say this device has output a wrong answer. Okay, right? If your task is to simulate yourself, then by definition you will always get it right? So I want an external standard of validation. Okay. And I would say that, for me, for quantum supremacy, we really need three things, okay? We need an actual observed speed up, as in we are doing something in minutes that would take, whatever days or weeks with the biggest classical computer that you've got on Earth. We need, but also we want it to be an instance of a general computational problem where we believe that quantum will give you an asymptotic scaling advantage, right? Where ideally that quantum is doing something in polynomial time that we think would classically require exponential time, right? Ultimately we are not after constant factor advantages, we're after a scaling advantage, or to do something in a few minutes that classically we think would take longer than the age of the universe or whatever. Okay, but then secondly, I want the first thing, the actual observed speed up, to only be explainable in terms of the scaling advantage of quantum computation. So in other words, I want a problem to be solved with let's say 53 qubits or however many it is, and I want the only explanation that anyone can offer for how it was solved to be, well, nature had this vector of 2 to the 53 amplitudes, which is about 9 quadrillion. They were maintained in a superposition state, and if I wanted to simulate that classically, we don't know how to do that without doing 9 quadrillion steps or something of that order, right? I would like to rule out any explanation for what happened other than that one. Okay?
I'm not sure if this rules out. At any given time, there's the fastest classical computer.
Yes.
Where classical is a special case of quantum, so you could say, well, that's
Yeah. So no. Bernard makes a good point here. So quantum supremacy is not quite like landing on the moon, right? It is a milestone that could be in principle be achieved and then unachieved, right? If, for example, someone discovers a much better classical algorithm in the future, or even if classical hardware just improves by some great leap. Okay. So it is a relative milestone. It is about beating classical computation, okay, and it is a milestone that is sort of relative to the state of classical computing power in the world today, and that is actually going to be an issue that will come up for us later. Okay. So yeah, the way I like to put it is that, for me personally, the number one application of quantum computing has always been, not, breaking RSA, whatever, I don't really, well, I'm lucky that I don't have secrets. I just put everything on my blog, but, I know other people have secrets. I guess that's important, but, it's not Grover speed ups for, AI, machine learning, whatever. It's not even quantum simulating quantum physics, which is probably the best hope we have to get something, really revolutionary for industry from a quantum computer. For me, the #1 application is just disproving these people who said that quantum computing could never work. That's Bob Laughlin, Nobel physicist, Robert Alicki, Michel Diakonov, some known to probably people here, Oded Goldreich, Leonid Levin, and Gil Kalai. And now the skeptics of quantum computing, in the wake of quantum supremacy, right? We should be clear that many of them can retreat to the position like, oh yeah, of course you could get quantum supremacy. No one ever said that you couldn't, even if in fact they did say that you couldn't, right? But but it doesn't count because until you have error correction, then it's not truly scalable, right? And so until you've got error correction, you've got nothing. I mean, certainly if I were a quantum computing skeptic, that is what I would be saying right now. Okay. Now, interestingly, that is not the position that Gil Kalai over here has taken. Okay. What Gil has said is that the Google experiment, the supremacy experiment they did, if it's correct, then it refutes his entire worldview. Okay, he had predicted that you would never get any quantum speed up. If they have, then he is completely wrong. The only possible conclusion, he says, is that Google must have done the experiment wrong. Okay, so like every week he has been emailing the Google team for more of their raw data and CCing me, and I guess he's going to find a student who knows how to code or something and do something with this data. But he is like 3 or 4 times said he thinks he found the crucial flaw and then taken it back. Now my opinion is that this is exactly what he should be doing. This is exactly how science is supposed to work. People should be trying as hard as they can to shoot the result down. So I am glad that someone with Gil's talents is doing that. Now personally, I would prefer to optimize not for the good of science, but just for being personally right. But, okay.
Can you
Yeah.
explain Gil's objection to quantum computing? Like in a high level?
You should probably have him do it, but he is actually said, yeah. Can I simulate him? Can I? Okay. So he has actually said that he thinks that quantum computing people should just continue to believe what they do and work on it. And in fact, there should be even more quantum computing research because it's going to be revolutionary for physics once it's discovered why he's right and why it can't scale. And then he just has like a moral obligation to sort of take the opposing side or something. So I say, okay, so you do you, and I'll do what you say that I should do, which is
The quality of their correction, like morally
Yeah. He thinks He thinks that error correction is impossible, but beyond that, he also explicitly said that he thinks that quantum supremacy is impossible, right? And he has some long thing about how if nature, the asymptotics he thinks can't possibly give this, and then asymptotics have to be reflected somehow in concrete numbers. And you should read his articles, and if you're able to explain it, then actually tell me, and maybe you can explain it to me. No. Also, the grounds of his objection shifts from year to year. So it's like Gil sub 2018 is different from Gil.
Right?
All right, fine. I've already been recorded saying so much worse that it's like at this point, who's counting, right? Okay. All right. So this brings me to the news articles that you probably saw a few months ago that looked like this about Google claiming quantum supremacy. Long story short, they sort of started down this path in 2015. Actually, after a sort of conversation that they had with some of us in the theory community about what would be a convincing demonstration of quantum supremacy. Okay, and which is a question that we will come back to. Okay. And so, we knew that they were working towards this, over, a time scale of a few years. This summer, they, thought that, they had it. So they said, but we're not going to have a press conference or anything like that. We're just going to submit, do the right thing, submit our paper to Nature for peer review. So, I was one of the reviewers. I had to, not blog about it and just sit on it, okay? But, what? Yeah, okay, fine. So, reviewing papers, fine. I guess, I guess even I know that I have to keep those things secret. But, what happened was that there were some co-authors of the paper from NASA Ames. So NASA had to do an internal review of the paper. As part of that, someone accidentally posted the paper on NASA's public website. They then quickly noticed that and they took it off, so it wouldn't have been a problem, except that Google Alerts found it. Okay, so Google kind of owned itself here. Okay, and then the Financial Times ran a story on it, and then all of the other press started running stories on it, and Google could not publicly comment on any of it because they were under Nature's embargo. Okay, so that was where my blog came in. I was not similarly constrained, so I could write about it, and sort of became when people wanted someone to explain it. Google could even unofficially kind of route some information through me. Okay, so. Okay, so what is the, but anyway, now the paper is out. It was the cover story of Nature for, I think, their 150th anniversary. Okay, so what are they claiming? Okay, so as I said, they built this Sycamore, this 53-qubit superconducting chip with controllable 2D nearest neighbor couplings. They used it to output samples from some probability distribution called D over 53-bit strings. Or rather not quite from D, but because of the noise in the circuit, from a distribution that is more like 99.8% the uniform distribution plus 0.2% the hard distribution D that you want. Okay, now that looks bad, but experimentalists are very used to signal to noise ratios like this one. Okay, now the good news is that taking each sample takes only about 40 microseconds, which means that in about 3 minutes you can take several million samples, okay, which means that a few million samples just by basic statistics is enough to actually extract the signal from a from a data set like this one, and that is exactly what they did. By the way, if you're wondering why it's 53 qubits, well, they built a chip with 54, arranged in a rectangle, and one of them didn't work. Okay. Okay, so they took about 5 million samples in 3 minutes, and then they did some statistics on them in order to extract a signal corresponding to this distribution D. We'll come back to that. And then they gave an argument that at least the best classical algorithms that they knew for sort of the general task of simulating their quantum circuit, and here they said, well, the best one we know is this algorithm from published in 2017 by Aaronson and Li Chen. So I guess I take some blame for this, but they said to run that algorithm on the biggest supercomputer that we at Google easily have access to, that has about 1 million cores, would take about 10,000 years. Okay, so that was the speed up that they were claiming. Okay. And they said, we expect that there will be faster classical algorithms discovered, but we also expect that the quantum hardware will improve and that the quantum hardware is going to win from here on out. We'll come back to that. Yeah.
Can you say, or will you say something about what this distribution D is?
I absolutely will. In fact, that's the next couple of slides. Yeah. So, all right. So why are we talking about sampling from a distribution? I thought, weren't you promised, Shor's algorithm for factoring numbers? Well, eventually that is exactly what one wants. Okay, but to really do Shor's algorithm in a way that would break, let's say, 2048-bit RSA, well, it requires a few thousand logical qubits, but with the known error correcting codes, that would translate into millions of physical qubits. Okay, so we're just eventually Shor, but we are no one is close to that yet. Okay, running Grover's algorithm, and even most quantum simulations also seem to require at least some error correction. Although for quantum simulation, there's at least a shot that you will be able to do something useful within the next decade. Okay, with only, let's say, minimal error correction. Okay. So what can one do in the near future then, or in the present? Okay, so this brings us to an idea that sort of emerged from the last decade or so of research in quantum computing theory. Okay, and this idea is to switch the focus from solving problems with a single right answer, like factoring, to sampling problems. Okay, where the goal is to output a sample exactly or approximately from some target probability distribution. But of course, such problems have a long history in CS as well. Okay, but what is the point of switching to these? First of all, it turns out that there are such problems that are much, much closer to sort of, what the hardware is natively doing, right? And it is just much, much easier to realize these speedups using these sort of noisy, non-error corrected quantum computers that can be built in the present. Okay, so that's the first thing. The second thing is, if all you want is evidence that you are doing something that is classically hard and you don't care what it's useful for, then it turns out that we were able to give pretty strong evidence that by the standards of complexity theory that these things are classically hard. Okay, so this is a line of work that, as far as I know, it started with a very prescient paper in 2004 by Barbara Turhall and David DiVincenzo. Okay, then the modern push to actually do this kind of sampling-based quantum supremacy experiment started with two papers in 2011. Okay, one of them was by me and my then student Alex Arkhipov, and it was on a proposal that we called boson sampling. Okay, which was a way to do this kind of hard probability distribution using, in that case, quantum optics. Okay, and that was then experimentally demonstrated so far with up to 14 photons. Okay, so to get to quantum supremacy, you would want at least 50 or 60. Okay, and then independently of us, similar ideas were proposed in what was called a commuting Hamiltonians model by Bremner, Jose, and Shepard. Okay, and in both of these papers, what we were able to show is that if you had, say, a polynomial time classical algorithm that could sample from exactly the same probability distribution as the ideal quantum computer would sample from, or from something very, very close to it, then the polynomial hierarchy would collapse to the third level. Okay, so that's bad, right? That's, by the standards of complexity, that's, close to the strongest evidence you're going to get that a thing is hard. Okay, now admittedly, in real life, you're not going to sample from the exact distribution, right? There's going to be noise. And so then, you have to ask, well, how hard would it be for a classical computer to sample from a noisy version of the distribution? And also, you never directly observe what distribution you are sampling from, right? So you have to apply some statistical test to the output, and then the question will become one of, well, how hard would it be for a classical computer to do anything whatsoever that would spoof that test? Right, so so we have taken up those questions. The hardness results we have. Well, I will come to them. They're not quite as good as what we have for the exact case. And I think one of the main open problems of this area is to get better results. But I will show. Yeah.
I thought that was for boson model, right?
So the thing about the polynomial hierarchy collapsing, actually, that kind of result can be proved for boson sampling. What we did for commuting Hamiltonians, also for random quantum circuits, that type of result is actually quite generic, right? Right. To get the more, like these were the first examples where it was shown, but the phenomenon ended up being much wider, right? What's trickier is to get the results about, let's say, evidence for hardness of noisy simulation, or for spoofing a particular test of, So, okay, so what are the disadvantages of these experiments? Well, first of all, until very, very recently, no one had any application for them. Okay, but secondly, there's an ironic issue where to verify the results with a classical computer, as far as we know, itself takes 2 to the n time. Okay, so what that means is that with 50 qubits, let's say, you can just barely do the verification with the biggest supercomputers that are easily available. Okay, you would not want 100 qubits for these experiments. Okay, because even if you had them, even if you did it right, you could never prove it. Okay, because you can't do 2 to the 100. Okay, so so these are experiments that are almost perfectly tailored for where we are now in the sort of the history of quantum computation. Okay, so now, to come to Bob's question, what is the distribution D that we sample from? Well, it's an almost embarrassingly simple proposal, right? But sort of what emerged in 2015 was that this was going to be easier for the Google engineers to do than boson sampling or, the things that, that we had proposed. And so, so they said, we're going to, do this, and then it's going to be your job to adapt the theory to the kind of hardware that we can build. We said we accept that deal. Okay, so okay, so basically you challenge the quantum computer by sending it simply a randomly generated quantum circuit C, on n qubits. Okay, the circuit will consist of a bunch of staggered layers of parallel quantum gates. Each layer looks kind of like this, and they are staggered in a way like that, so that after I stack enough layers, then every qubit is able to sort of influence every other qubit. Okay, and then we start the circuit in the all zero state. We apply these layers of gates. That produces some complicated, entangled state on n qubits. We then measure that state, to get a random string of, in this case, of 53 bits, okay, which will be sampled from some distribution D depending on the circuit C. I'll call it D sub C. Okay, and we record our random choices so we can then take more and more independent samples from the same distribution D sub C by running the same circuit over and over again. Okay, so let's say we ask for k samples, k independent samples from D sub C. I'll call those samples S1 up to S sub k. Yes?
Is the quantum circuit encoded classically or generally?
It is, yes.
Okay.
Yeah. So the description of the quantum circuit is something classical. We generate it on our classical computer using whatever random number generator we want, which could be a quantum generator, but doesn't have to be. We then see, yeah. Okay, so and then we have to, given these S sub i's, we have to apply some statistical test to them. So, are these sort of good samples that actually, solved a hard problem? So how do we do that? Well, so the test that Google ended up applying is one of the simplest things that you could write down. It is what they called the linear cross-entropy test. I won't even go into the reasons for the name or historical. Okay, but all that it means is that using brute force on your classical computer, you calculate the predicted probability for outputting each of those samples S sub I, right? That's what this, quantity here is, right? Just the probability that if I started with the all zero state, applied my circuit perfectly, and then measured, that I would see S sub I, okay? And then I just sum all the numbers up for I equals 1 up to k, and I count the test as accepting if and only if that sum exceeds some threshold. Okay, so what am I doing here? Well, intuitively, the better the quantum computer is, the larger should be this sum. Okay, why? Well, because, the distribution D sub C, is some kind of total mess, okay, but it is not the uniform distribution. Okay, so, it has little wiggles in it, okay, and, the reason is that, among these 2 to the n final amplitudes. Some of them, each one is like a sum of many, many contributions that are all just, pointing every which way. And so for some of them, the cancellation of all those contributions will be a little bit more perfect than it is for others. Okay? Or to be more precise, we can model each final amplitude as being like an independent complex Gaussian. right? And actually, in some cases, this can now be that statement can now be rigorously proven. Well, they're not quite independent, but they're sort of quasi-independent. Okay, in some cases, that fact can be rigorously proved, even when it can't be proved. It is known to be true by way of MATLAB. Okay, but you know, so then you know the probabilities are these squared absolute values of these independent Gaussians, which are actually exponentially distributed random variables. So, you know, basically all the probabilities are exponentially small, right? They are all of order 2 to the minus n. Okay, but some of them are 3 times 2 to the minus n, others are 1/2 times 2 to the minus n, and so forth. You know, they vary by, constant factors, okay? And so what we're trying to do here is say, have we preferentially output the samples that were supposed to be likelier, okay? And now we can calculate. Suppose that I had just I just output the SBIs completely uniformly at random. Well, then the average probability is of course 2 to the minus n. So if I added up k of these things, I would expect to get k over 2 to the n. So in other words, I would expect to only achieve this if b equals if b is less than or equal to 1. Okay, now suppose I had an ideal quantum computer. Okay, well in that case, what value would I expect to see for this sum? Well, now it's just an integral that you have to do. Fortunately, it was an easy enough integral that even I could do it. Okay, and the answer that you get is 2k over 2 to the n. Okay, so you get exactly, the ideal quantum value is exactly twice the trivial value. Okay, if you like.
Ideal quantum value.
Meaning if I had a noiseless quantum computer. Okay. Now, what you'll achieve, in reality, with a noisy device, is something in between 1 and 2. Okay. Long story short, what Google has reported in its experiment is a value of b that is 1.002. Okay, so as you can see, that is quite far from the ideal value of 2. Okay, and basically this is because the fidelity of the experiment, until you have error correction, it is decreasing exponentially with the depth of your circuit, right? The depth of the hardest circuits they could do while still extracting a signal was 20. Okay, so they've got a depth 20 circuit, and and that's why they end up with a signal that's only about 1 in 500. Okay, but that was still a signal that they could extract. So in other words, they could still collect enough statistics to prove that that 1.002 really was larger than 1. Okay, and if any of you have seen like the Bell inequality, that proved that entanglement was there, right? That followed a very, very similar story. It's very analogous to that somehow. Okay. So John Martinez, who was the head of, in charge of the experiment at Google, likes to use the analogy of speckle. So if I took a laser pointer, like this one, although I don't know if it's worked. What? Okay, all right. Well, you know what a laser pointer looks like. If I sent some laser light through some ground glass, I would see a pattern like this one. There are certain spots where there is more constructive interference among all the paths that the photons could take through that glass. Okay, those are the redder spots. There are also sort of black spots where there was more destructive interference between the different paths. And what this means is that if I just sampled a bunch of photons landing on this screen, I could check for consistency with the speckle pattern by seeing, did the photons preferentially land in the redder spots? So that's exactly what we're doing here, except that in this case, our screen has a size of 9 quadrillion, okay, of 2 to the 53 power. Okay. All right, so now that was Google's claim. Now, some of you may have seen that even before Google's paper officially came out in Nature, IBM posted a rebuttal paper. Okay, IBM happens to be Google's main competitor in superconducting qubits right now, and their initial response actually was, we reject the entire concept of quantum supremacy because all that matters is solving practical problems for our customers. Okay, and and to me that was like, well, before you even worry about, like ferrying passengers around in a plane, you first prove that your plane can fly, right? And then that just seems completely obvious, right? And so I was not impressed by that, okay? But then, a few weeks later, maybe recognizing the unsatisfactoriness of that response, they came out with a more robust one, which is, well, we don't think Google achieved quantum supremacy anyway, okay? And their argument was, well, look, Google estimated 10,000 years for simulating their chip with a supercomputer. However, if you took Summit at Oak Ridge National Lab, which IBM just installed a year ago, so they know about it, and which is the largest supercomputer that currently exists on the planet, okay, which it's got about, fills 2 basketball courts, okay, it's got about 100,000 cores. More relevantly for us, it has 250 petabytes of hard disk, okay, and what they said is, well, that is actually enough hard disk that you could just take a vector of 2 to the 53 complex numbers and just explicitly write them all to hard disk. Okay? And once you had done that, then simulating Google circuit will be a simple matter of a few matrix vector multiplications. Okay, so you can do the naive Schrodinger simulation, of just update the vector and so forth, and you don't have to use the fancy algorithm of Aaronson and Chen, right? And and that they estimated would take only 2.5 days. Okay, which of course is better than 10,000 years. Now they didn't actually do this. Summit is being used for like nuclear weapons stuff. It's not so easy to commandeer it to just prove that Google will prove a point about quantum supremacy. Okay, but I will accept for the sake of argument that something like this would work. I think that it was embarrassing on Google's part that they overlooked it. They were only thinking about storing stuff in RAM and not writing 2 to the 53 numbers to hard disk. Okay. But I would also say that if this is the strongest objection, then, well, the way I put it is that it's a little bit like the Kasparov versus Deep Blue chess match, except with the historic irony that IBM is now in the role of Kasparov. Okay, so it's like with heroic effort, you can, just, almost match what the, what this Sycamore chip is doing with literally the largest supercomputer on the planet. Okay, if you added just a few more qubits to the Google chip, that already would not fit in the hard disk here, okay? And with 60 or with 70 qubits, then forget it, okay? So yeah.
So who even said the 2.5? Like, what's the difference between 2.5 days and 10,000 years? Is there a cutoff? Like. Yeah,
right. Well, it's not clear. I mean, notice 2.5 days still is a lot more than 3 minutes, right? Yeah. So these I just want right. So there's no official line for quantum supremacy, right? I want to see a separation by some number of orders of magnitude, right? But if you say we're going to multiply the classical cost by the number of cores in this thing, right? By the energy that it takes to run it, and so forth. Well, then that certainly makes the speed up, considerably greater, right? Because the Google thing is literally just one chip, right? And a dilution refrigerator, is somewhat energy intensive, but a lot less so than this thing. Okay, so it actually costs less to run. The quantum computer, yeah.
Would your algorithm do this faster? I mean,
the point of, okay, so this brings me to the next slide, actually. So here are the trade-offs that we know, right? What are the best classical algorithms that are known for simulating general quantum circuits? Well, there is this naive Schrodinger simulation, I said, which would use 2 to the n time and also 2 to the n memory, right? That's just, I write the entire quantum state to memory. Okay, more cleverly, there's what you could call the Feynman sum over paths, which will be way more memory efficient, use only linear memory, but the time it will use will be even worse. It will grow like 2 to the number of gates, right? And we're talking about 1,000 gates in this circuit, okay? So Google can do 2 to the 50, but not even Google can do 2 to the 1,000. You might say that exceeds a Google. Okay, so Li Ji-Chen and I a few years ago asked the question, could you somehow get the best of both worlds? I don't know why that question was not asked earlier, but we proposed an algorithm which is actually very, very simple, divide and conquer, inspired by Savage's theorem in complexity theory, okay? And, we just solve a recurrence and we get an algorithm with linear memory and with d to the n depth, where d is the depth of the circuit. Okay, so that was our thing. Okay, but you notice that none of these breach the 2 to the n barrier, right? And like from my point of view, as long as we're not breaching the 2 to the n barrier, then it's clear that for these sampling problems, the future belongs to the Sycamore, like superconducting quantum computers. Okay, so. Okay, so of course this raises, from my point of view, the central theoretical question here is, well, can you breach that 2 to the n barrier? Could there be some much faster classical simulation algorithm that nobody has thought of yet? Okay, so of course we don't know the answer to that. But the one thing you might worry about is even if we can't simulate like a general quantum circuit, maybe there's a classical algorithm just for the narrower task of spoofing Google's benchmark. It would just find some S1 up to SK that scores well on their benchmark, and it only did that. Okay, so we at least have a theorem that addresses that worry. Okay, so Li Ji-Chen and I had such a result in our 2017 paper, which was, that was for a different benchmark than the one that Google ended up using. Recently, Sam Gunn, who is an undergrad at UT, and I adapted the result to the specific benchmark that Google applied. Okay, and our result basically says the following. Suppose that there existed a classical algorithm to spoof Google's linear cross-entropy benchmark, efficiently, or let's say even just in much less than 2 to the n time. Then there would also exist a classical algorithm, running in a similar amount of time that could take a random quantum circuit C and that could estimate a specific output probability, such as the probability of outputting the all-zero string, and it would have a really terrible variance, but its variance would be just slightly better than that of the trivial estimator that would always guess that this probability is 2 to the minus n. Okay, the variance would be about like 8 to the minus n better than that. Okay, but actually, the only algorithms that we know get a variance that is better than that of the trivial estimator by an amount that is exponential, of minus m being the number of gates. Okay, so as long as the number of gates is large compared to the number of qubits, then we don't know how to violate this hardness conjecture. And what we're saying is that if you're going to spoof Google's benchmark, then you must make some headway on the general problem of estimating an amplitude in a random quantum circuit, which is not something that we quite know is sharp P complete. But if we change the problem slightly, it would become sharp P complete. Yeah.
Can the Google computer do any circuit, or is it only got specific configurations that they can do, which might be easier?
Well, so what they can do is they can vary the couplings, of the gates that they're applying, right? So it's like they only do the nearest neighbor interactions, but by varying which gates are being applied, within each layer, you actually, in principle, you get universality. Right? Okay.
Is it a fixed 2x2 matrix that's doing the coupling, or
oh yeah. So actually the way they do it, I believe, is that the couplings are, there are a particular 4x4 matrix, right? And actually they engineered it just because they were they originally had one where there was a classical algorithm called tensor networks that would just be able to simulate it in 2 to the power of the number of these gates, and they didn't like that, so they changed their design, just to evade that algorithm and make it 4 to the power of the number of gates, right? So they've made engineering decisions just for the purpose of getting faster to quantum supremacy, okay? But now the thing that you can vary are sort of the 1 qubit gates that go in between the 2 qubit gates, okay? Which again is enough for universality.
Confused about something. So
yeah.
How much? Let me ask it this way. So
yeah.
How much work was it to compute that cross-entropy thing classically?
2 to the n.
Okay.
Well, I mean, let's say it is 2 to the n if you have enough memory to write it down. If not, it could be even more than 2 to the n. But yeah.
So they had to do a lot of work.
They did. Oh yeah. So I should mention that Google actually did not directly verify its hardest circuits. Okay, they relied on some extrapolation where they say, well, we make the circuit easier to simulate in a way that obviously does not affect the fidelity, and then we get the answer, and we go up to almost the hardest, and we directly verify that, and I was not completely happy with that. Now, one of the big ironies of the IBM response paper is that Google could now say to IBM, hey, this is great. Now you can go and you can verify our hardest circuits for us. Yeah.
In this notation, 2 to
Yeah.
the n and 2 to the n over 2 are
Yeah.
the same thing? Or?
No. One is the square root of the other one.
But
What?
in those calculations.
Sorry. No, I just don't understand the question.
Well, and
Yeah.
so
Yeah.
for sampling,
Yeah.
it's like instead of breaking the system, you're
Yeah.
just trying to find the collision, maybe.
So
that's like 2 to the n over 2.
Are you? Yeah, but that would assume that you had a quantum computer to do the sampling with. All right, I'll be happy to talk about it offline, right? But you can't even take one sample in the correct way, without with a classical computer, without as far as is known, without doing a hard computation. That's like 2 to the n. Okay. All right. Now the until very recently. Oh yeah, sure.
So while verifying the random circuit for the quantum
Yeah.
quantum
Yeah.
so do you not have to verify the distribution of the circuit? Like what's the distribution?
Yeah. So in this case, you could say that the challenger was Google itself, right? We are trusting that Google really did generate the circuit randomly, as they said they did. Now, it would be better to have an independent, entity generating the challenges, which actually brings me to the final thing that I wanted to talk about. Okay, which is that until very recently, an obvious objection you could raise to this is even assuming this supremacy experiment works seems obviously useless because all you produce are these strings that are basically random, right? They're not uniform, but it requires this massive computational effort even to distinguish them from uniform. Here's what some random bits look like if you haven't seen them before. Random bits, right? That just seems pretty useless. Okay, now the new idea that I had just a couple years ago is that actually random bits are not totally useless, particularly if you can prove to a skeptic that you must have generated them randomly. Okay, certified randomness could actually be useful, and as sort of a byproduct of this sort of sampling-based quantum supremacy experiment, a very interesting thing that you get from it is sort of complexity theoretically certified random bits. Okay, so why is that? Well, let's say we send a challenge to the quantum computer, sample the output distribution of this circuit, and let's say that it passes it. Okay, it passes this linear cross-entropy benchmark, right? Well then, it is, the original point was, it is proven up to complexity assumptions that it must have been a quantum computer in the first place, couldn't have been a classical one. Well, that's great. But now even a quantum computer, suppose that it wanted to pass the test in a secretly deterministic manner. Right? How would it do that? Well, it could try to find the largest probability outputs or something, but we expect that to be an intractable problem even for quantum computers. Okay? So now under some complexity assumptions, some admittedly very strong ones, but I was able to show that even a quantum computer, if it is going to quickly pass the linear cross-entropy benchmark, it can only do it by sending you samples from some distribution that has a large min entropy. Okay, so it has a lot of actual randomness. Okay, it might not be exactly the distribution D that you wanted. For example, Google could just keep taking samples and only send you the ones whose first bit is a 0 or something silly like that. Okay, but notice that even in that case, it would still be sending you a lot of random bits. Okay, and so then these are not uniformly random bits, but once you have a string with a lot of min entropy, as many of you know, you can then feed it into a well-known classical tool, a seeded randomness extractor, okay? And with a small initial investment of randomness, you can then get out a lot of nearly perfect random bits, which you could then use for cryptographic applications. Okay, so what applications do we have in mind? Well, anything where you want like a large, let's say, public source of certified randomness. So for example, these proof-of-stake cryptocurrencies, right? These are things that try to do something like what Bitcoin does, except without using 1% of the world's energy to invert a hash function, okay? And but what these do require is a huge source of public randomness, to constantly run lotteries to decide who gets to add the next block to the blockchain. Okay, and and everyone has to trust that this randomness really is random, even though you're just getting it off the internet from somewhere, right? That it's not secretly pseudo-random and predictable by someone. Okay, so you could use these quantum supremacy experiments for that. Now the idea that you could use quantum mechanics to get random bits is an old and an obvious one, right? If you built your own hardware and you trusted it, well then just send some photons into a 50-50 beam splitter and you're done, right? Voila, randomness, right? It's built into quantum mechanics. We are trying to solve a different and harder problem here, which is how do I prove that these bits are random to someone else over the internet, okay? And, and if we can respond quickly to these challenges in a way that passes the linear cross-entropy benchmark, then in a way we are also certifying randomness. Okay, so UT has actually licensed this to Google. Now, this is, I thought that in my career I would, have like 0 patents, so now there's 1, okay? But Google and NIST are actually working right now to demonstrate this protocol. And it is not by far the most impressive application of quantum computing, but it looks like it is the first application that will be realizable. Yeah?
Is it not a problem that the cross-entropy benchmark is hard to...
It is a problem. It is a problem. What it means, but the good news is that the verification is something that you can do at your leisure, okay? And we could do it with like, let's say 50 qubits, so that it is within the power of a supercomputer to do. Furthermore, you only need to do the verification for a tiny number of the samples of the rounds, right? And then you are statistically confident that there must have been a lot of min entropy in most of the rounds, right? Which is all that you need, right? So you can just verify a tiny number of the rounds. You can do it later at your leisure, or you could even threaten that you might do it, right? In order to keep the quantum computer provider honest, right? But yes, having said that, yes, it's a problem. And one of the big open problems is, can you do this in a way where there's efficient classical verification? Yeah, I would love that. Yeah, Mark.
Is there a family of algorithms where you could use a downstream quantum system to call D into a much smaller this source of D, and
yeah.
Presumably you could use some interference to...
Yeah, I don't know. I mean, people have discussed things like, could you use one quantum computer to verify a supremacy experiment done by another quantum computer? I actually don't know how to do even that right now, okay? But we can talk about it offline, right? I mean, I think these are great problems. There are lots of exciting places to go next from here. I think it would be great to replicate Google's result in other hardware platforms with higher fidelity, more qubits, and so forth. I think we should work hard on designing new classical algorithms for simulating quantum circuits. I mean, the fact, that we could discover new things about that question in recent years is exciting, but it's also disconcerting, right? It means people have not looked at this enough, okay? And then in the other direction, of course, we want better complexity theoretic evidence for hardness of, simulating random quantum circuits, okay? And then, we just touched on this, but I think what has emerged as one of the central theoretical open problems in this whole area is, can you get quantum supremacy with like a noisy near-term quantum computer, but in such a way where a classical computer can efficiently verify the result? Without having to do a brute force computation. There was a proposal for this a decade ago, due to Bremner and Shepard. Recently, that proposal was broken. Okay, and but I would love more such proposals. Yeah.
Is there any way to any reason to believe that maybe this is impossible?
I don't know.
The other way?
I don't. Yeah, it might. I don't know. But one thing we know is that eventually, once you have a scalable quantum computer, well, then you can run Shor's algorithm, and then factoring is efficiently verifiable, right? It is an NP problem. The other thing we know is that again, once you get a scalable quantum computer, there is this beautiful recent work by Urmila Mahadev, right, which has shown how you can take any quantum computation and then by using lattice-based cryptography, extremely clever ways, you can make its answers verifiable by a classical skeptic. Okay, so you can take any quantum. She showed how to take any quantum computation and make it verifiable. Okay, but again, that probably only kicks in once you've got a fault, once you've got an error-corrected quantum computer. Right. So here I'm asking what we can do in the near term. So it's it's a little bit of an ill-defined question, but with something like these sampling experiments, let's say. Okay, and then there are lots of open questions about my randomness protocol, about how to actually get a reasonable bit rate and actually make it useful for someone in practice, for cryptographic applications. So. Conclusions. Google has apparently achieved quantum computational supremacy using random circuit sampling on 53 qubits, building on a lot of the airy-fairy, useless complexity theory that we did over the last decade. Even if true, this leaves the enormous challenges of getting to scalability and fault tolerance, but I think it already refutes those who said that quantum speed-ups were fundamentally impossible in our world. So it was thought obvious for years that sampling-based supremacy experiments had no applications. The certified randomness protocol might change that, although, as I said, many challenges remain in making it practical. Okay, so thanks for listening.